So bounded linear operators. So we all know what the definition of a linear operator is. I give some arguments here. So L, we'll say, goes from a norm linear space X to a norm linear space Y. So X has some norm X, and then Y has some norm Y involved with it. And then if I have L of alpha be some scalar, V is going to be some vector in X plus W equal to alpha L of V plus L of W, just classic linear.
You have such an odd way of lecturing. You'd like write down the specifics after the property. I mean, it's fine. I obviously know what you mean, but like,
yeah, sorry.
I just no. Everything's good. Everything's good. I just found it funny how you like introduce X and Y after you defined.
Sorry, I'm sorry about
L,
that.
X and Y.
So
I always understand what you mean. I just wanted to.
Oh, for sure.
That was really funny. So.
All right, I'll write it down first, and then I'll talk about it.
Yeah.
Sorry about that. So then what we'll do is, so this is just definition of linear. So now we're going to talk about what it means to be bounded, which essentially is given by this definition, that if I apply, so let X be some vector in X, and if I take the norm of L of X, this lives in Y, there's going to exist some number C greater than 0, so that's always bounded above by M times the norm of X, right? Or sorry, C. And this is an X. So this is what we'll say is basically, this is the definition of bounded operators. If you can find some number C such that the norm of L of X is bounded above by C times norm of X. And then there's some clean properties that we can talk about for bounded linear operators. And this will give us a proposition. So let's say we have L from the normed linear space X to Y. We have a norm in X and a norm in Y. And then the following are going to be equivalent. L is continuous at 0. If that's true, then that's equivalent to saying that L is continuous on all of X. 3, that there exists some C greater than 0, such that L of X is less than or equal to C times X. And this is for all X element of X, just that the norm of X is equal to 1, less than or equal to 1. And then we can actually extend it even further, that there exists a C greater than 0. Maybe I'll call it M. It doesn't have to be the same C as over here, such that the norm of L of X is less than or equal to M norm X for all X. I don't care about the norm or anything. For all X and element X. Just a quick question. Has anyone here taken like a functional analysis course and seen all of this sort of stuff before? Here and there? Do you guys want me to go through these results?
Well, isn't 3, I don't understand how 3 isn't evident for.
Oh, so in this case, what I'm restricting to is purely X is norm less than or equal to 1. Think of this the sphere inside.
Yeah,
sphere
but
norm
that's
1.
also contained in 4, no?
Yeah, and in this case,
Oh, it's like
in this case, I could go to even bigger norm vectors, but still, you find an M such that that's always true. It's always bounded above the M times norm X with these norms like in X and Y. Okay. And then from this, so I won't go through these. I'll just basically we're just going to be using this argument and this argument. And because they're all equivalent, this is basically saying that if you're working with linear operators, if it's linear and bounded, it's immediately continuous. They're all equivalent. You can prove 1 to 2, 2 to 3, 3 to 4, or back to 1, or vice versa. Right? So bounded linear means continuous. So we're going to be using that a lot. Because that means I can exchange limits inside and outside L. So then from here, what we can kind of see as well, I've defined bounded operators, but I have to keep track of basically x I'm plugging in, right? So we say as well, this C here is kind of defined like a supremum, right? That no matter what I plug in, L of x may be less than this, but if I can find this C, I know that this could act as my supremum. So what we then do is create this operator norm, which we define as L operator is equal to the supremum for all x less than or equal to 1 of L of x. Right? And then from here, what we can then say is that, well, this should be less than or equal to, if you can find me the value C, then I can at least say that this is bounded above by C. Right? It might be smaller than C, but at least I know that's bounded above. And then what we can also prove is that, well, here I'm very explicit in that I'm talking about vectors of norm less than 1. This is also equal to supremum over norm x equal to 1 of L of x. And it's equal to supremum over norm x not equal. So vectors whose norm is not, what should I say? X not equal to 0, x an element of x of norm L of x over. These are all equivalent definitions. That I won't go through, but basically what I want to use here, sometimes one of these definitions is more applicable to a problem, but they're all equivalent. They can choose whichever one makes a proof of it easier. Basically, what you would do is just show that this is a subset of this is a subset of this, and it's just a bit of arguing over what belongs in what. You assume it belongs in one set, show it belongs in the other one. You kind of do some manipulations by picking x and y, normalize them in some way, and then you can show that they each contains each other. It's not too difficult, it's just kind of annoying to work with. So I'll just we'll take that for granted. And then what I wanted to talk about is wanted to compare this to what we have in linear algebra when we work in finite dimensional cases. So that's usually where this is coming from. We're kind of just extending linear algebra to infinite dimensional spaces here, right? So we have a very common or very simple result for bounded linear operators. In finite dimensions. So if we have x and y are norm linear spaces, so I'll use NLS to mean norm linear spaces, norm in x and a norm in y. And then if we have any linear operator L from x to y, where L is linear, then we have that L is bounded. And we'll denote bounded sets by this B of x comma y. So B is a bound any, is a set of all bounded linear operators from x to y, just that L is bounded. This is a notation I'll be using from now on. I'll just say L as an element of B of x, y. And then I'll also use B of x, which is equal to B of x of x, so match from x to x. So here, essentially what we're going to do is, I'll prove this result. Essentially what we're going to do is, because we're in finite dimensions, I can pick a basis for x, pick a basis for y, and I can use the fact that because I have a finite basis, I can write all my norms in terms of L2, right? And then from L2, I can then basically just work with vectors, makes the proof very, very simple. So let's say I have, so since x and y are both finite, I can say that I have some basis EI, mine is 1 to n, which is the basis for x. Then I have a set of fj, j equals 1 to n, which is my basis for y. So then what I can do is I can say I have some vector x. I can rewrite it as a finite sum of some scalars ai EI, I equals 1 n. And similarly, what I can then do here is I can use the equivalence of norms, where we can say that the norm of x in x is equal to this finite sum of AI, EI of I, x. I can bound this above or below by some alpha, some x of this vector A, where A I define to be basically a column vector of these components here. So A1, A2, an. So then this is, I'm sure you guys seen this in real analysis. 351 or so, or maybe 333, I forget which one you
I
guys
was
have seen.
studying, I don't know.
Oh, you're studying it?
Yeah, I haven't taken the.
Okay. Right, so what I'm basically saying is that, okay, if I have a norm in x, what I can then do is essentially I can just work with the component vector here. I can always find this scalar, so I just bounce this from below. And then I can just work in Rn all the time.
Now, can you rate your indices a bit bigger
Yeah,
so the camera can pick it up?
A sub I. All of that.
Okay.
And then what we'll do then is say, okay, well then, if I do L of x, what I can do is rewrite that as L of a sum A I I. L is linear, so I can pull sum out. So it's equal to sum of I, A I, L E I. Right? So then what I want to do is I want to show that L has to be bounded. What I have to do is somehow show that I can find an upper bound of L of x, some m with this balance, this, so I can find this value of m. What we're going to do is basically relate it back to these coefficients here. So here, what I can do now is I can take the norm of L of x, I can take norm of this. What we have here is that L of EI, well, these are elements in Y, right? So I can write them in terms of this basis Fj of Y. We can then do, and so this is the norm over I, and then this is a norm sum of A, M, so I, M. Right, for each EI, take a sum over these FMs, and you get back L of EI. So this I here just takes into account that it's a different basis vector. Okay, perfect. And then now what I can do is rewrite this as essentially sum over of something I'll call gamma m. And this belongs to Y. And what I've done is I've just combined these coefficients together, just to make the proof a little bit simpler from here on out. So we have is that this belongs to, I'm taking a norm over Y, where I'm taking these components, right? Just as here, I can bound it below, I can also bound above by some other scalar, and bound this above by what I'll call beta Y of the norm of gamma, of this vector gamma, I take a true norm. For the Euclidean norm. I'm using this gamma vector is just these components. So now what I can do is, well, taking a two norm is pretty easy, and I can just plug in what each component is here. So this is equal to beta Y times sum over m. Norm of each component for each m is given by the sum over I of AI, AMI. Okay, sum over I of A and I, AI. Squared. And now what I have here is I have a sum over I, two numbers, A and I's, and I. What I can use here is I can actually use Cauchy-Schwarz inequality, which tells me that, sorry. that this is bounded above by the sum of I, A, and I squared. There should be a factor of one, raised to 1/2, but this square is going to take care of that. Times norm of I of absolute value of AI squared. And there should be a factor of 1/2 here, but this part takes care of that. What I can do is bound this above like this. This is less than or equal to beta y times the sum over m of sum of I, A, and I squared. And then we also have the sum over I, A, I squared. Now here we can see is that this term here does not depend on m. I can pull it out this sum. So now what I have is basically I have a double sum for this term here, where the sum over m and i's is less than or equal to beta y of sum over m over sum over I of A m I squared 1/2. Then here I have sum over I A squared 1/2. But here this is just the norm of the two norms of the vector A. But from our result over here, I have that the two norm is bounded above by the norm of x. I just have to divide by this scalar alpha x. What I have here then, that this is bounded above by beta y over alpha x times this double sum here times the norm of x in this vector space x. Right, so what I have here then is that L of x is bounded above by this number times x. So what happens for finite dimensional cases, for the finite dimensional case, every linear operator is bounded. Every matrix we've ever worked with was bounded. Right, so then the reason why I want to show this is because a lot of results I'm going to be showing, you're going to see, oh, this is true linear algebra. We've seen it a bunch of times in linear algebra. They all hold true as like a special subcase, right? Whereas every result I have in finite or infinite dimensional cases, because they're bounded, all these results also hold for the finite dimensional case for free. I just want to show this just so you can kind of see this, how you find these upper bounds. Okay.
I mean, the extension into the infinite dimensional case is definitely non-trivial.
Oh, not trivial, for sure.
Yeah, okay.
Yeah.
I was gonna say, like, you definitely can't do any of this for.
You definitely got it. There is a thing I will talk about called maximal orthogonal sets, where basically kind of generalizes this idea of bases, but that's why Hilbert spaces are really nice.
Yeah.
Because if you have separable Hilbert space, it guarantees that there is a maximal orthonormal set, so you can kind of do this stuff. But still, non-rigorous. So taking a sum of an infinite number of terms, you have to then show that they converge. There's some nice results. Yeah, we'll go through it a little bit and we'll kind of see the nitty-gritty of why things fail. Okay, so yeah. So we talked about bounded linear operators. Now, a special case is, well, if I have a linear operator, in what sense can there be an inverse of a linear operator? Right, it's a pretty common result. If you have an inverse, there's a lot of problems you can solve. You can invert problems, you can find, and you solve problems pretty easily. But the issue is, when do inverses exist and when do they exist for interdimensional problems? So here I have, so first I'll define what an inverse is. So inverse of an operator. So let's say T from norm linear space X to Y. X and Y are norm linear spaces. So then what we can say is that T is invertible if there exists a T inverse such that T of T inverse equals the identity on Y, or sorry, X, and then T inverse of T is equal to the identity on Y. So essentially, you need to check and see if you are right inverse and the left inverse. In the case of finite dimensional cases, you show one, the other one's already true. In infinite dimensional cases, you have to show both. So then, under what cases does this inverse here exist? And more importantly, under what cases is the inverse also bounded? And this, we can use this very easy theorem where, so the theorem is given by, if I have T, which is a bounded linear operator from X to Y, where X and Y are both non-linear spaces or norm to linear spaces. Yeah. If T, yeah, so T has a bounded inverse, if and only if T is bounded below. So by bounded below, I mean to say there exists some small m greater than 0, such that T of X is greater than or equal to m times the norm of X for all X an element of X. So if I am bounded below, then that gives me immediately that T has a bounded inverse. By bounded inverse, I simply just mean you take T inverse of Y, where Y is an element of the image of T. Then there exists some capital M greater than 0, such that M bounded from above. Essentially, if T is bounded below by small m, there exists a big M, so the T inverse is bounded above. This
relationship between the two terms or no?
Yes.
Oh.
So what we have then is we can actually compute what the operator norm of T inverse is. It's exactly equal to 1 over the infimum over all norm X, 1 of Q. So essentially, you find the infimum of the all of the lower bounds T of X. So basically, find the infimum of all of these m's, compute it here, and then you get the upper bound of T inverse. Right, so they're kind of related.
Is
So-
it upper bound or is it an equality?
Equality, exactly equality.
Yeah, it's the equality between the capital letter.
Yeah,
All right.
essentially, this may not be the infimum, right? Just a lower bound, right? But it guarantees that there is an infimum, right? And then if you can compute what the infimum is, you'll be able to get what the upper bound of T inverse is.
Yeah.
Right, now we can go through the proof. So we'll do the forward direction first. So we suppose first that T has a bounded inverse. So what that tells us then is that so let's take Y as an element of the image of T. So since Y is an element of the image of T, that means that there exists some X such that T of X equals Y. And then what we're assuming is that T inverse is bounded linear. So BL, we use short for bounded linear. So that means that T inverse of Y, since obtaining bounded linear, there exists some M. So this is bounded above by M of Y. But Y is an element of the image of T, so I can now just plug in T of X. T inverse of T of X. Well, that's just equal to X, which is then bounded above by M times Y is T of X. I can move this M over here. That immediately tells me that 1 over M norm X bounds T of X from below. Right, so now what I've shown is that if T inverse is bounded linear, right, then T has to be bounded below. right? So this is the forward direction done, and now we'll do the backwards direction. So what we do is we suppose t is bounded below. T is bounded below, which immediately tells us that t of x is greater than, or there exists some small m greater than 0, such that t of x is bound, or m times norm of x is greater or less than or equal to t of x, all x equal to big X. So then what we can do is we can say, okay, well, if I want to show that t is invertible, one criteria I can do is check and see if it's at least injective. Then there's a one-to-one mapping, so then I can always map from the image space back to the original space. So let's assume that z is an element of the kernel of t. That means that tz has to be 0, and we're assuming in this case, let's assume z is non-zero, right? Let's see if the kernel is empty or not. So then what we'll do is say, okay, well then, tz is going to be equal to 0. I'm assuming that's in the kernel, but it's also bounded below by m norm z. I'm assuming in this case that let's assume that z is not equal to the 0 vector. The norm of z is not the 0 vector. And m, I'm assuming, is greater than 0. When I have 0 is less than or equal to some positive number. So I have a contradiction here. So that means that the kernel of t has to only be the 0. What I have now is I have an injective function, right? I have an injective function, one-to-one. I can always find an inverse for it if I only work in the image space t, right? So then,
Is it sufficient for what we want in terms of a bounded inverse?
so here, the only thing I've shown is that the inverse exists. Right now, I have to show that it's bounded, right? Okay. Yeah, so we have t is bounded below. So then let's take y, an element of the image of t. So again, that means there exists some x, element of x such that y is equal to t of x. So then what I have here then is that t inverse of y, which is then going to be equal to t inverse t of x, that's assuming equal to the norm of x. And then because we have that t is bounded below, that means that from this result here, x is bounded above by 1 over m t of x. 1 t of x. And then what we have is that, well, t of x is equal to y. So this is less than or equal to 1 over m t norm y. Then I have t inverse of y is bounded above by 1 over m norm of y. So now what I have is t inverse is bounded above. So now we show the phenomenon. Right. Now I'm going to introduce a new space, which I'll call the dual space. So let's say we have, let me source this one. Okay. So I introduced this notation of beta or b of x y, where this is the set of all L of x to y such that L is bounded linear. And then what I'll now introduce is this new space called x star. So this we'll call the dual of x. And this is equal to beta of x real. So it's the set of all bounded linear operators L from X to the real numbers, where L is bounded linear. Good. And then what we'll talk about is, so here I'm just, basically just a special case of bounded linear operators. So essentially, you just take an element of X, and then L is map it to some real number. Kind of like dual spaces when you work in quantum mechanics. Basically, you have cat X, which lives in H, and then you introduce this dual X to an element of H. The dual H, right? This eats X's and spits out a real number, right? So that's kind of what we've introduced here, but just in a more general sense. We'll talk about this near the end. Okay. So then the reason why I want to introduce this is because, well, the set of linear operators here we can treat as a vector space, right? If I can give it a norm, maybe we can talk about whether or not this space is going to be Banach or not. And small hint, this operator norm that I've introduced here actually makes our space beta of x comma y into a Banach space. Beta of x comma y with the operator norm that actually is a Banach space. So if I have a Cauchy sequence of operators here, so let's say I have a set of bounded linear operators in beta of x comma y. Then I can talk about sequences here converging, talk about Cauchy, and talk about whether or not they're going to converge in beta of x, y, or if they converge outside of it. In this case, if you use the operator norm, they'll always converge in beta of x comma y. And then we'll just go through some simple properties of this. So let's say, proposition. Let's say I have sequence Tn, which converges to T. And then I have in the operator sense, operator norm sense, then I have a sequence Sn, which also converges to something in S. Both of these are in the operator norm sense. Now what I can think about is, well, their composition. Let's say this is from beta of x comma y, and this is elements of beta of y comma z. So I can think of a composition of them. So Sn composed with Tn. That was reasonable assumption. So does this converge to St, the operator norm sense? In this case, it does. I'm going to show that pretty easy just by using squeeze theorem. So if we take the operator norm of Sn of Tn minus St, the operator norm sense, we can then show that this is equal to, so here we'll use, well, we're just going to basically add and subtract by, we're basically just going to add 0 to the Sn Tn minus Stn plus Stn minus St. And then what we can do is use triangle inequality. Because the operator norm is a norm, we can apply triangle inequality. We say that this is bounded above by Sn Tn minus Stn. Here we can see that we're going to try to factor out this Tn here plus Stn minus St, the operator norm. And then what we can do is this is equal to Sn minus S N plus S equals to
Should be in the column.
oh, sorry, yes. Okay, and then what we're going to do is use like there's one result I forgot to talk about the composition of S and T. So if we take the operator norm of a composition ST that's bounded above by the operator norm S and T, and the way we can check that very easily is the definition. So we take S composed with T, which by definition is equal to the supremum over all x less or equal to 1 of s of t of x. What I can then do is say that this is bound to the supremum over s of t of x. If s is bounded, then I can bound this above by the supremum over norm s, norm t of x. If t of x is also bounded, a linear operator, and this is bounded above by the supremum over norm s, norm t, and then norm x. So what I have here then is that essentially s of t operator norm is bounded above by this. It may not be equal to the operator norm of s of t, but at least it's an upper bound. So then I can then use, so this is what we call submultiplicative. It means the operator norm is submultiplicative, where essentially if I have two things under the operator norm, then multiply together, or in this case, composition, I can then just write them as the product of the two operator norms. That's what we call submultiplicative. Here I have two things that lie in that are bounded operators. Here, Sn minus s, both Sn and s by assumption are bounded linear operators, and Tn and T and s here are assumed to both be bounded linear operators, and use a submultiplicative definition here, where I can say this is bounded above by Sn minus s norm n plus norm of s Tn minus t. And then what I have to assume, well, something I made here is that Tn converges to T, Sn converges to S in the operator norm sense. Therefore, if n goes to infinity, this will converge to 0, while this is going to converge to norm of T. This is just some number S, so it doesn't change, but this will go to 0, and this will also go to 0. So what I have is that this is bounded above by 0. Every norm is also bounded, bounded below by 0. The norm can never be negative. But if I squeeze theorem, they converge. So if essentially this is just that common limit definition. You have two sequences, the limits converge, and the product of them converge to the limits. Essentially holds true here. Okay. Right. Now we're going to go into an interesting example. So you've probably seen in a lot of your ODE classes this idea of matrix exponentials and stuff, and they never talk about, well, is it well defined? Can you actually define a matrix exponential? People say, oh, in analysis you can prove that it converges. In this case, with the idea of operator norms, you can't show it converges. And in this case, we're going to use a really, really simple result. So first, what I'll do is I'll define this beta n, which is defined to be equal to a partial sum of k 0 to n of a matrix A to the n over n factorial. Yeah. And then what we're going to do is show that, okay, well, if A is an element of a bounded linear operator.
In finite case?
No, in this case, different case.
Okay.
Yep.
I was gonna say the finite case is probably easy to show converges because you just diagonalize the matrix.
Exactly.
Yeah.
Right, in this case,
Convergent every term, but yeah.
yeah, in this case, no idea what to do, right? So then what we'll do is, so then let's see if this sequence converges. Since I know it belongs to B of x, comma x, and we know that if I use the operator norm, this is in mono space, and I can show this is Cauchy, then immediately I have convergence, right? So let's see. So let's say Bm minus Bn. And without loss of generality, just assume m is bigger than n, so that everything, I can actually write out what this is equal to. So this is just going to be equal to finite sum from k equals n plus 1 at m of a to the n over n factorial operating on. Now what we're going to do is use triangle inequality, so we're going to pull the sum outside. This is bounded above by sum from k equals n plus 1, the n of a to the n over n factorial. But we talked about, well, what is a to the n? A to the n is just equal to a composed with a composed with a n times. So then what we do is use submultiplicity of the operator norm. So this is bounded above by k equals n plus 1 the n of a to the n over n factorial. Right? But then what is the operator norm of a? That's just some real number, right? So essentially we can consider this as just some, call it alpha, yes. K equals n plus 1 n of some real number, or let's call it n. So what we would say is that a, the operator norm, is always less than or equal to some big n. The n factorial. And then what we have here is essentially just a outstrips. Or essentially it's just the sum of exponentials with a real number, where n is a real number, right? And then this here, because we know this series converges, right? Then we know that, well, it converges in a real number, therefore it's Cauchy. Therefore this is a Cauchy sequence. So as m and n go to infinity, this goes to 0.
So there's another equivalent definition for the operator norm being like the largest singular value. Then
Yes.
is that related to the other ones that you defined, or is that restricted to the finite dimensional case only?
The operator norm?
Because like now I'm thinking with these proofs and using operator norm, I'm thinking the supremum, the
Yeah.
ones that you told me. I should be thinking about that one, right?
Yeah, no, you can actually compare, you can compare them to the singular values as well. Essentially what you do is you take, I think those should be, yeah, I think those might be in the finite dimensional case, but I don't think
Yeah,
you
I'm
can
trying to
do a
think-
singular value
Yeah,
decomposition in
yeah,
infinite dimensions.
Yeah, okay,
For compact normal operator to take like the maximum eigenvalue.
okay, like even, oh, okay. Even.
Yeah, that's when the compact normal operators are always diagonal.
Okay.
Yeah. Okay. Take your word for it.
Yeah, so then what we have here is that, so you guys remember the result that the space is monic if and only if every absolute sequence converges, or
Every
sequence converges
converges
absolutely,
yeah.
right? So what I have here is a Banach space, and then I have that the absolute, or absolutely, yeah. So this sequence is absolutely convergent, right? So what I do here is I have a Cauchy sequence that bounds this from above. So now I have that this is Cauchy because I live in a Banach space. That means this converges. So if I take a limit as n goes to infinity, this is actually well defined. So what we can do is just say, okay, well, this is, we'll just define it to be as n goes to infinity. Define this to be equal to e to the operator a, right? So now what we've defined is essentially what it means to take an exponential some operator here. This could be a matrix, finite dimensional case here. I haven't talked anything about dimensions here, but we know for finite dimensional cases are immediately bounded. So this result holds there. The only assumption I made here is that A is a bounded operator. This could also be Y, doesn't matter. Is that good? Yep. Okay. And now I'm going to do another example where I talk about von Neumann series. This one is similar to what I've done here, except if anyone's taken any sort of, I want to say, have you seen this in your functional analysis class? Maybe did you take with Matthew Kennedy?
No.
Oh, yeah,
It's with Michael Brennan's term.
Oh, okay. I know Matthew Kennedy would have enjoyed this because he just had through operator problems on our assignments, but like hit him in the notation. So none of us knew that that's what he was testing us, but it's like, oh, this is a simple quantum result. Well, it turns out you need functional analysis to actually prove it rigorously. So, so what we can do here is, okay.
Did you take 731?
Yeah.
Okay.
So what we can do is, okay, we'll take X to be Banach space. And we'll take A, the element of the boundary operator of X to X. And we'll say that the operator norm of A is less than 1. Then what we're going to do is we're going to define a partial sum as from k equals 0 to m of ak. Right? And then this is an element of the x, because essentially what we have here is that the norm of ak is less than or equal to the norm of ak, which is still less than or equal, less than 1. Right? We've bounded, so the composition of these are still bounded. Therefore, there's in the bounded linear operators from x to x. So then what we want to show first and foremost is, well, does this partial sum converge? Can I take the limit as m goes to infinity? And the way we're going to do that is check and see, first and foremost, is it Cauchy? So what we do is we say, okay, b of m minus 3n. So this is given by, without loss of generality, you can just assume m is bigger than n, so we can actually evaluate what this partial sum is. Goes from k to n plus 1, m, with a to k. So now what we can do is then, again, same tricks we did before, right? We use triangle inequality to pull the sum to the side. This is less than or equal to the sum from k equals n plus 1 to m, norm of ak. Then we can do is the norm of a to the k using the multiplication. We can say that that is less than or equal to k equals n plus 1 to m, norm of ak. But we have that the norm of a is less than 1. So this is just a geometric series. Right? So what I can do is I can just bound this above by 1 over 1 minus norm of a. Right? So I have basically that this partial sum converges. It converges in the real numbers. Therefore, this here is Cauchy. Right? So therefore, this here also has to be Cauchy. Right? So what I have then is that I have a Cauchy sequence in a Banach space where I use the operator norm. Therefore, this sequence converges. Then what I can do is I can actually take the limit as m goes infinity, and it converges to something in beta of x comma x. So what I can do is I can say, okay, well, let b be defined to be equal to the limit as m goes to infinity of the partial sum a equals 0 to m a to the k. What is this equal to? We'll just define it to be equal to k equals 1 to infinity of a k. Now the question is, well, what does it actually converge to? I know it converges, I just don't know what it converges to. Right? So then here's where the interesting part comes in. Or why this partial sum is of any interest to anybody. Yeah. If I take I minus a times b, I will show that equals the identity. So essentially what I've shown, oh, and then you take b times I minus a, that also equals the identity. So I've shown that b is the inverse of I minus a. Right? So just we'll go through showing this one because the other case basically goes the same way. So I minus a times b, well, that's equal to the limit as m tends to infinity of I minus a partial sum from k equals 0 to n of k. So now the reason why I wanted to do this is just so that I can multiply through without having to worry about limits or anything. Here this converges, therefore the limit of the product also converges. So what I can do is the limit and then distribute this through. So I have a to the k equals 0 to n minus k equals 0 and k plus 1. Yep. Okay. So then what I can do is now, what I'm going to do is I'm going to try apply a index shift here. So then what this is going to become is essentially, if I define k prime to be equal to k plus 1, then k prime starts at 1, goes to, yeah. And then this is a k prime. But then what I can do is I can shift this down to 0 and subtract away the identity. Right? Then this is equal to the limit, I'll do it one more underneath, is equal to the limit as m tends to infinity of k equals 0 to m of k minus k prime equals 0 to m of k prime
Okay, yeah.
minus the identity. Minus times the minus gives me I. This term cancel. This is just equal to the limit as n tends to infinity of the identity. Right, so I've shown that B is a right inverse, but here we can see that if I apply it on the left, the sum just moves to the left side, the result is still the same. So I've shown that it's both right and left inverse. So what I've shown here is that I minus A inverse is equal to B. Right? So then as long, and the only restriction I had here is that A is a bounded operator, and that the operator norm is less than 1. So here essentially in the real number, like if this was essentially what you can see here is that to even show that the partial sum converges, all I have to do is relate it back to a geometric series. Right? So here it kind of looks the same, right? As long as A is less than 1, in which is a geometric series, perhaps the value of A is less than 1, the geometric series of A converges. The operator norm sense kind of behaves the same way. There's a kind of a parallel you see where a lot of results in the real numbers are going to hold for matrices. And it's because the operator norm works so nicely. Right? Not everything holds true, but a lot of similarities where you can kind of just be like, oh, if it worked before, it's still going to work. But there's some nitty-gritty details that we have to deal with. In this case, we have to deal with the fact that, well, they're not numbers, but once you use the operator norm, everything becomes numbers. So you can actually evaluate these. So then the reason why I wanted to go over this example in particular is because for this next example I'm going to go through. So this here is really important for the idea of perturbations, where essentially, let's say you have a nice operator, which is invertible. But then I tweak it a little bit. I add like a new operator plus s. Well, if it was originally invertible, under what conditions for s is it still invertible? Right? The really common question that I'm going to use that you may see in quantum, but usually you see it in numerical methods courses. So let me just introduce the problem first. So, let's suppose P and T is invertible, and they're both elements of bounded with your operator to max x. And then we assume that x is 1. This ensures that theta affects the operator norms. This gives us that this ensures that this is in Banach space. And then let's say, okay, let's say I take T and I just apply some new operator S, and we'll define this T epsilon. So T, we assume is invertible and has a bounded inverse. And I apply this little S here, right? Usually we talk about you basically nudge it a little bit by S, but in this case, what the hell does little mean? So what we're going to say is that the norm of S is small. And we'll have to kind of figure out how small it can be, and we're going to derive that together. So then what we can do is say, okay. Okay. So since T here is invertible, what I can do is I can actually pull it out. So T of the identity plus T inverse of S. Since T is invertible, this is well defined. We'll multiply through and just get back to T plus S. Okay. Now what we're going to do is we're going to define this to be minus, or we're going to define this to be minus A. So this is equal to P times identity minus just A. Okay. So based off of this example here, yeah. So under this example here, what I can do is I can say that, go back one step. So my question is, okay, if I know T is invertible and I just nudge T by S, under what conditions is T sub epsilon still invertible? So if T sub epsilon was invertible, what we can then say is that, yeah, if I can, if it was invertible, then I need T to be invertible, which is given, but that means I also need this I minus A. I need this to be invertible, right? I minus A. Under what conditions does the inverse exist? But from right here, we have that I minus A inverse is equal to B under what condition? That the norm of A is less than 1. Here I've defined A to be T inverse of S. So that means that if I want the norm of A to be less than 1, that means I need the norm of T inverse of S to be less than 1. Since I've assumed T inverse is bounded, that means that this sufficient condition for this to be true is if T inverse norm of S is less than 1 over T inverse. So under this condition, this isn't if and only, but if this is true, then this is true, then this is true, right? Then I have that this inverse exists. This inverse exists. I know T is invertible, and T sub epsilon is also invertible, right? So if this condition is true, then I have that T sub epsilon is invertible, and we can compute the norm of T sub epsilon and its inverse. So in this case, let's see. Yeah. So assuming this condition holds true, what I can then do is actually write out what T sub epsilon inverse is, which is just equal to I minus A inverse T inverse. I minus A inverse, we've shown here, is equal to the limit of this partial sum here. What I can do is rewrite this as A equals 0 to infinity of A to the K times the inverse. And in this case, I have that A to the K is just simply given by T inverse S. This is equal to the
Can I ask a question?
K equals 0 to infinity of T inverse S K. Inverse of the inverse. What I can do is just expand out the first couple of terms of this absolute. When K is equal to 0, this is just, you can define any operator to 0 to just be an identity. This is just the inverse. Plus minus. Sorry, I need the minus sign right here. Minus T inverse of S the inverse. And then plus T inverse S T inverse as the inverse plus blah blah blah. Just keeps going on. Then what we can do is I can pull out the T inverse from the left-hand side. This is equal to T inverse of identity plus S T inverse plus S T inverse S T inverse minus dot 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 plus minus will keep changing. And then what I can do here is, well, this is T sub epsilon inverse. And then we can take the operator known of this.
A.
William asked, didn't we have I minus negative a?
I minus negative a. Yeah, so what we've done here is we have I minus negative a.
He's asking why. It's because we proved it.
Oh, yeah, we proved it for I minus a, but in this case, we had t times I plus t minus s. So I just introduced two minus signs. T minus one.
I don't know if that's what Will was asking.
Was that?
I'll see what Will says in the chat.
Okay.
You can continue.
Oh.
I'll tell you when Will answers.
For sure.
Yep. Oh, he said on the current board we have I minus a instead.
Oh,
The last, yeah.
Oh,
but
oh, sorry. Yeah, this would be I. Yeah, absolutely. What I've done here is just I've defined a equal negative t inverse s, which is
okay, fine, yeah.
yeah.
Yeah. Because then so then that board is technically ruined. Because then you should have removed mine. Yeah.
Sorry about that.
But if you leave that, then now you're good.
Now that should be fine.
Yes.
Sorry about that.
No, Will says, oh, so it's a different a.
Yeah. It's a
Yeah,
different-
well, now he's fixed it.
Yeah,
When Will asked, they
Yeah, absolutely. I'm sorry about that, Will. Yeah. So essentially, we've done is t sub epsilon is t plus s. And because t is invertible, we can pull t out from the left side. So identity plus t inverse s. So what we do is we define this to be negative of negative t minus s and define this to be a. So now I have identity minus a. And then under the condition that norm of a is less than 1, is the inverse of I minus a is just equal to this sum. Yeah, so then, yeah, so essentially what we've done here is using this von Neumann series. We know under what conditions or for what value operator s is. If you nudge an invertible operator by s, under what conditions is t sub epsilon still invertible. So this you can kind of see its applications in numerical methods. I had an example where I was going to talk about resolvents. So this is sort of stuff you guys would have seen in quantum theory 2 with Graham Smith. No? All right. I would have talked about that, but I'll have to wait till the end, or if I can even get to that point, because it's pretty interesting. Essentially, you turn an operator problem into a complex analysis problem. And then for people who take complex analysis, contour integrals all the way, you find residue, yeah, use residue theorem to basically find your single, your singularities, exactly.
Or I guess the poles.
Yes, exactly. And then your poles will be your point spectrums, and then there's actually a really nice way of seeing what it means to be in the resolved set, the continuous set.
Wait, but like, don't you define the poles as being like, 1 point? How do you be in a spectrum? I think the order of poles, like, a second order poles, third order poles, blah, blah, blah.
Not so much. It's let me see. Yeah, from here pretty much. Yeah, so we've shown the inverse. So I'll talk about that a little bit. I think.
Okay, wait, before you read, okay, that's fine.
Sorry.
Where, like, S we understood was like less than 1.
Yeah, so we
That
have
was one of the
that.
conditions for
We have
invertibility.
t inverse s has to be less than or equal to 1 because I defined this to be the norm of a. And then we said, okay, well, I don't know what s has to be here in order for this to be true, but we showed that, okay, well, since t inverse is bounded, I can say that t inverse.
Yeah, I get all this, but
yeah.
like, my question was more like, when we talk about perturbations of things, don't we like just innately require that our perturbation is small?
Yeah, the issue is, what the heck does it mean to be small in the sense of an operator?
Oh, I see.
Right? That's one thing I always hated about courses where they say small. You nudge it by something small. You see in calculus variations, but you nudge it a little bit, right? And everyone says, what's that little bit? Okay, well, you take 2 endpoints, you have this, and then if you want to find the, the Lagrange, you want to find a stationary point, like, oh, then nudge it just a little bit by a new curve. But it's like, what does it mean by nudge by a new curve? It's like, oh, you just apply epsilon times an eta, where it still satisfies the boundaries, and then you add it to whatever the solution is, which you call epsilon, or not epsilon, wait, gamma or something. Gamma is the one is your stationary curve. You nudge a little bit there, but no one ever talks about what it means to nudge something. What does it mean by nudge something small? In this case, kind of like, oh, you're just multiplying it by some small scalar. What the heck does it mean in the operator sense? Especially if I'm working with them into an infinite-dimensional space. What the heck does it mean to be small in that case? Right? So in this case, we're talking small. I wanted to bring emphasis to small in the sense of the operator norm. And then, yeah, so one sufficient condition is if I have the operator norm of S less than 1 over the norm of T inverse.
Yeah,
Right?
okay.
And then bringing back to that theorem I had, well, T inverse, when is this bounded? When T is bounded from below. So these theorems can basically be used in conjunction with each other, right? And this is really, really, really important for numerical systems.
So you said it wasn't an if and only if statement, right?
Yes. If T is bounded below, then T inverse exists and is bounded above if and only if T is bounded.
Yeah,
above.
that was if and only if.
Yeah,
The inequalities that were on that board where it was like S is bounded by 1 implies T inverse is.
Oh, yes, yeah. This part was just
one way.
yeah, we don't know what S has to be, but if I have this condition here,
Then it's sufficient.
then it's sufficient.
Okay,
Right?
yeah.
Right, yeah. Doesn't have to be this, could be something else, but this is sufficient for our problem. Okay. I'm gonna erase everything here. So far, actually. No, okay, so I really want to get to resolvent sets because that's the whole point of this talk. But I probably won't have time to get there. But just quickly, how many of you guys remember what you learned in quantum theory 2? Do you guys remember the whole resolvent
Yeah.
stuff and how you guys have Occam for that?
Well, I had Occam, so
Yeah.
we're like spectral.
Right, and then at some point he talks about how, like, you probably introduced it but never really went through it, and then no one really talks to you about what the heck a resolvent is. How it's the inverse of basically your eigenvalue equation.
Yeah.
That,
Oh, yes, yeah, I remember now.
Right, so we say-
We barely did that, right? Because it was like the one part where it's not invertible or invertible, yeah. I remember.
Good. Thanks. Now we get to some of the fun stuff, which is this new set of operators, which I'll call compact linear operators. So how many minutes do you guys remember compact from real analysis? Not the topology, I guess it's equivalent to the topology way, but set is compact if you can find a subsequence that converges within the set. So then what we have is we have a definition for compact linear operators. This is just a simple definition. So if we have T from X to Y, where these are normed linear spaces, T is compact if for all bounded sequences X of I to subsets of X, we have that the set T of Xi to subset of Y, that there always exists a subsequence which converges in Y. This subsequence we say converges in Y. So the limit of E of X of K, as K goes to infinity, is an element of Y. So it doesn't have to converge into the image of T of X, but at least within Y. So here what we're saying is basically that T is compact if it maps every bounded sequence to a relatively compact sequence or set, sorry. Right, so then we'll go through a really simple example. So easy example is the identity a compact operator. What do you guys think? Right. So then, that's right. So the identity is not a compact operator, and it's because the unit ball in infinite dimensions does not have to have a convergent subsequence. Essentially,
Really?
Yeah, so I'll go through the proof. Just one quick question. Do you guys ever do Riesz's lemma in analysis?
Okay, wait, which one are you talking?
This was the one where, I'll just state the theorem. So Riesz's lemma. We have is, okay, so let Y be a subspace of a nonlinear space X such that Y is strictly subspace X. So it's not the entire space. Y is closed. And then what we'll do is we'll define D X comma Y is equal to the minimum of the elements of Y norm of X minus B. So then what Riesz's lemma basically says is that, oh, sorry. And then here, X has to be an element of Y. Oh. So then what Riesz's lemma basically tells us is that if I have, so if I let this parameter lambda be between 0 and 1, then there exists an element of Y complement, where the norm of X is equal to 1, and the distance of X, comma, my closed subspace Y is strictly greater than lambda. Essentially, you can basically just think this is saying that you can get basically as close as you want to Y if you're not in Y. Basically, that's all this lemma is saying. And the important part about this is we can talk about what happens with a unit ball. So, so what we'll do is we'll show that for a unit ball, so let's take a sequence of X, I, where the norm of Xi is equal to 1. So everything basically lies on a ball of radius 1. Then what we'll do is we'll say, okay, well, so we'll let A be equal to the ball of radius 1, which is given by all points whose norm is 1. And then what we'll do is say, okay, well, we'll pick one element in the ball, call it x1. So the norm of x1 is equal to 1. And we'll call y1 is equal to the span of x1. Right, let's see. Because in the span of x1, y is going to be closed, because anything in the span of x1 is given by basically just a sum of x1. So anything in this span is going to be generated by x1 if it's an element of the span. Therefore, any sequence here, if it converges, has to be written in as a span of x1, so it's within y1. It's a subset of x because here it's only one element from A. And yeah. So
your Riesz lemma.
Yeah.
What if Y contains the unit ball? Why?
Yeah, sorry. Y is closed.
Sorry, again, that's not what you mean. Again, no, it's fine, it's fine.
Oh,
Yeah, you already wrote it before, sorry.
okay. Yeah. Sorry, is there anything?
Oh, yeah, it's fine.
Okay. Yeah. So then, yeah, okay. So then, based off of Riesz's lemma, I can take something that's not in Y1, such that the distance between, so there exists some x2, an element of A, such that x2, the distance between x2 and x1 is greater than lambda. I'll say that's 1/2. Yeah. So then what I can do is then define y2 to be equal to the span of E of x1, x2. Right? And then here again, I have a closed subspace, which is a subset of A. And then what I can then do is say that, okay, well, there exists an x3 such that the distance of x3 from y2 is greater than 1/2, which essentially says that the distance between x3 and x2 is greater than 1/2, and the distance of x3 comma x1 is greater than 1/2. Right, and I can do that continuously. Right, and because let's say if I'm working in infinite dimensional spaces, I can always continuously do this. Essentially, I'm using the fact that I have infinite number of directions to pick out these xi's. Right, continuously do it. Well, okay, let's make a sequence of these xi's. Right. Now, okay, well, that means that, okay, well, let's say I take xn and xn. They're distant. Well, from here, it's always greater than 1/2, right? Can't be Cauchy, right? Therefore, can this sequence ever have a convergent subsequence? No, because it's never Cauchy, right? So it can never be convergent, right? So then what I've shown here essentially is that the identity on a bounded set A is just everything has norm 1, which if this is equal to A, it can never be relatively compact. It can never find the convergent subsequence. Right, so shown here essentially that the identity map is not compact, right? Which is pretty interesting in itself. Is use the identities, use the easy map you would use. It holds a lot of cool properties. In this case, it doesn't hold because it doesn't preserve, or it's not compact. And then here, big reason why I wanted to go through this example is just to show that the in infinite dimensions, bounded does not mean compact or even relatively compact. And here's a pretty simple counter example, but you need some extra machinery here, which is recent fun. Not too hard to prove, but it's one of those like nitty-gritty ones where you kind of just have to work with inequalities. You just have to work with inequalities. So, does that make sense? Yeah. Pretty serious. So then, okay, well, if the identity is not a compact operator, how the heck can I even check and see if something is compact without having to check and see every bounded sequence, right? So here we have some simple theorems. So the first theorem relates what happens when we have a finite range. So let t from x to y be bounded linear. And then x and y are normed linear spaces. Then we have that suppose that the dimension of the range of t is less than infinity. Then we have that t is compact. Right, so this theorem is pretty simple. So it just says that if the image is finite dimensional, then T, if it's bounded linear, has to be compact. So again, come back to finite dimensional case of matrices, always compact. Right, so a lot of results we have here for finite dimensional cases or for linear algebra just hold true. I won't go to the proof of this. It's kind of nitty-gritty, but simple enough result. Right. Now, what happened? How do you deal with the infinite dimensional case? And this is where you have to be, you have to show a bit of ingenuity. So, there we go. Here. This one actually I have a name for, so it's a sequence of compact. The sequence of compact linear operator. So, so let X be a Banach space. And then let's suppose I have a set of Tn, so a sequence of them, where they're bounded linear operators from X to X. And let's say that this set of Tn converges to some operator T, which is also bounded linear. Then if the Tn's are compact, then T is compact. So essentially what we have here is we have a sequence of compact linear operators. And if they converge to T with respect to the operator norm, then T has to be compact. And this proof, sorry, Dan, how much time do we have left?
You got 20 minutes.
20 minutes. I'm going to skip the proof just because it's just a bunch of epsilon delta definitions. But so in this case, essentially, if I can create a sequence of bounded linear operators and I can show that it converges to bounded linear operator T, then I know T is immediately compact. So this is again, this is where infinite-dimensional dimensionality really messes things up. It's not super easy to show T is compact, but there are for Hilbert spaces easier methods of showing T is compact, which I'll try to get to now. All right. So yeah, so here we're gonna now introduce. Here we're gonna move on from norm linear spaces and start working with inner product spaces. Let's say we're gonna culminate to Hilbert spaces. Resource. So, for inner product space, we have a vector space and we incorporate some inner product. And then we have some simple properties. So just to make sure we're all on the same page, we're going to use that it's conjugate linear in the second variable. So if I have x plus alpha z y, that's equal to x comma y plus alpha z comma y, and then we have x comma alpha y is equal to alpha bar x comma y. For here, x, z, y are elements in our space X, and alpha is just some complex number C. Okay, and then we have some simple properties. So we'll say that X is orthogonal to Y, if X comma Y is equal to 0. Then we say that, okay, well, the inner product helps us induce a norm. So the norm is equal to X. And then we have the Cauchy-Schwarz inequality, X comma Y. Absolute value is less than or equal to the norm of X times the norm Y. And then we have that X comma 0 is equal to 0 comma X, which is equal to 0. And then the other result is that if X comma Y1 is equal to X comma Y2 for all X, this is the is that Y2 equals 1. And then, so this is a pretty easy result to prove. Essentially, move this inner product to the other side. So you get X comma Y1 minus Y2 is equal to 0. Since this is true for all X, you can plug in Y1, Y2 for X. Y1 minus Y2, Y1 minus Y2 equals 0. The left-hand side is Y1 minus Y2 norm squared equals 0. If the Y1 minus Y2 has to be the 0 vector, the Y1 equals Y2. Really simple result here. But the most important result is I want to show is that you can move the limit inside and outside of an inner product. So if you have that xn converges to x, you have yn converges y, then you have that xn comma yn converges to x comma y.
If you can write a little bit bigger than.
Oh, I guess for sure. So is that too small?
Yeah, but it's fine. From now on.
Right, this one's a bit bigger. So xn converges to x and yn converges to y. Then you have that xn comma yn converges to x comma y. So essentially, you can pass limits in and out of the inner product. And in this case, assuming y was just a constant sequence y, you can move it into the left argument, or vice versa, you can move it into the right argument, linear both arguments. Okay. So then, so then I'll define what a Hilbert space is. So Hilbert space is just an inner product space. So H is a vector space, you add an inner product, and you make a product, so it's complete, right? So that's basically all you need for the Hilbert space, right? And then this comes with a lot of properties. So the first one I'll talk about is Hilbert's orthogonal projection theorem. We'll just these ones I went through, but I'll just state theorems. So, sorry, Vaughn, when you learned, did you ever talk about Hilbert's projection theorems or decomposition theorem with the convex sets? All right, perfect. All right, so here. So let Y be a closed linear subspace of H. So H I'm just going to designate as a Hilbert space. And then let X be an element of H be given. So this is just some given element of X, or sorry, H. Then the following hold. So we have that one, there exists a unique element Y, element of our closed subspace of H, such that the distance between X minus Y is actually equal to the minimum over all elements of Y of X minus Z. You guys remember that B of X comma Y, which was defined equal to the minimum over the element of Y norm of X minus Y, or B, sorry?
Yeah.
Oh, sorry, I just want to say. Right. So in general, it would be the infimum, but in the case of Hilbert spaces, it's a minimum, and it's obtained within the closed linear subspace Y of H. Right, and it's also unique. And because of this uniqueness, what we can actually denote is what we call the projection of X onto Y, which is just equal to Y. Essentially, you take X, there exists a unique vector Y such that it's the minimum distance between X and our space, our closed subspace Y. So then if you project, we call this projection operator onto the space Y of X, we project X onto Y, it's just equal to this unique element. Right?
Sorry, I thought it was like capital Y again, like,
Oh,
confused.
sorry.
Yeah, no, that makes sense.
Okay. Yeah, so then we would call this essentially, you can call it your orthogonal projection. We'll have to figure out what it means to be orthogonal in this case. And that's given by the second property, 2, which is given by the fact that this element Y, element big Y, is the unique vector such that X minus Y is an element of Y prime. Okay, so this is basically why I want to talk about this is like the orthogonal projection of X onto Y. because x minus y is an element of y squared. And then so essentially what we have here then is that if we take x minus y and inner product it with some vector v, where v is an element of y, right? This is always going to be equal to 0. And then the third property here is essentially that if I have any closed subspace of H, I can decompose H into y directs on y further. Right, so this is basically the decomposition theorem or Hilbert's decomposition theorem. And in the case of so this is pretty strict in the sense that it's a pretty big assumption to have a closed linear subspace. Turns out it's true if you just have a convex.
Yep.
Convex set. That's the only, that's actually all you need to prove this theorem. This is basically,
Closed linear implies convex.
sorry?
Closed linear implies convex. Or
Yeah.
is it just
Yeah, because essentially the subspace, right? You can take any linear combination. For convex, you can only have if x and y element of H and H is convex. X lambda plus 1 minus lambda y is an element of H.
Yeah.
This is all you need.
Yeah.
Right, if I have a subspace, I can take any combination, this is all you need to actually prove this, right? I'm just going with this case, it's, again, we work with subspaces all the time, this is just like the proof you only need this result here, okay? All right, I'm not gonna prove this theorem just because it's actually pretty long.
Yeah.
If you replace y to be convex, you would have to take the closed linear span.
This one here.
Yeah.
Yeah, exactly.
Yeah.
Essentially, if I was to go through the proof, there's a step in here where essentially you just need the fact that 1/2 x plus 1/2 y is an element of H, and then that's it. That's it. This is the only term that you just need to show as an H, and then you can basically prove it. And then, so essentially, you go through what I think is actually, if you actually Google Hilbert's projection theorem, you only need a convex set. It's a much stronger assumption. But I'm just gonna work with it because we're working with subspaces regardless. Right. Now, based off of this theorem here, we have Riesz's representation theorem. So this is technically a quantum theory 2. If you took it with, I think Eduardo, he would have talked about this. I don't know why Occam never wanted to deal with it, but essentially the theorem tells us this. So Riesz's representation theorem. So let x stars, this is that dual space I introduced a little bit ago. So this is equal to the bounded linear operators from x to the reals. Yeah. So then, so let H be your Hilbert space. And so then we have these properties. For all y elements of H, we can define this linear operator Ly, which goes from H to, essentially you can call it K, but this will just be either the real numbers or complex numbers, whatever you want to do, but I'll just use K, just be a bit more general. You can define Ly of X to equal X comma Y. And then this is an element of dual space. So for any element Y and element of H, you can always map it to something in the dual space. And then we have an extra property that Ly, the operator norm of Ly, is equal to the norm of Y. And then the second property is the fact that if you have for all f an element of the dual space, there exists a unique element Y, element of H, such that f of x is actually just equal to this element. Right? So now we have kind of the converse, right? For every y, I can define this linear operator in dual space given my inner product. Conversely, if I'm given anything in the dual, I can actually just rewrite it as an inner product uniquely from X to Y. Essentially, what I've shown here then is that for every element Y and H, I can map it to something in the dual given by this. Similarly, everything in the dual, I can then remap in terms of Y and limit of H. So what I've shown here then is that I have an isomorphism between H and H dual. And then I think this is something, Polygon geometry or differential geometry kind of do that, where you take anything, any vector, then you can map it to the dual, right? And then based off of like those bases that you guys use.
Yeah.
Right?
Yeah.
Kind of same thing.
You also have a functional analysis.
Yes. Right. Is there much on that one? I'll fix the proof of this.
Few minutes.
Right. And then, so essentially, just to talk, so this theorem here, which is called Hilbert's projection theorem, proving this, you can then prove Riesz's representation theorem, and then from Riesz's representation theorem, you can prove the existence of adjoints. So, let T go from H to H, be bounded linear, so BL. So basically, T is an element of theta of H. And then what we have is that we have that T star exists T star is an element of B of H, it's bounded linear as well. And the operator norm of T star is acted as equal to the operator norm of T. And in this case, I will. You guys want to see the proof of this one? Basically, essentially, you use Hilbert's projection theorem to prove Riesz's representation theorem, and from Riesz's representation theorem, you can then prove the existence of adjoint. And the only restriction here is that T is a bounded linear operator from H to H. Right, so here you don't even need compactness or anything like that. You just need the fact that it's bounded linear. And then in this case, all I just prove this theorem because it's kind of nice. So first things first, just to make sure everyone remembers what it means to be an adjoint. If I have T of X comma Y for all X comma Y and element of H, this is equal to X comma T star of Y. Right, so essentially I can just move the T to the right side because basically the adjoint just allows me to switch which vector is being transformed. So, right. Yeah. So then the proof of this is actually pretty simple. So let Y be an element of H. And then we're going to define this operator L Y from H to complex numbers given by L Y of X is equal to T X of Y. All right, so here we can see is because T is bounded linear, this operator is going to be also linear. And we also have that I take the norm of Ly of X. This is equal to the absolute value of P X comma Y. And here I can use Cauchy-Schwarz, which tells me this is bounded above by T X Y. And then since T is bounded linear, it's bounded above by the operator norm of X, operator norm of T, norm of X, norm of Y. If you group these two terms together, so this is equal to norm of T times the norm of Y, norm of X. But here I have that Ly of X that is bounded above, or the operator of Ly is bounded above by operator norm of T and this given Y, right? Just an arbitrary Y. So that Ly is bounded in your operator as well. And then, yeah. But we have that, okay, well, yeah. So what I have here then is
William asks, why is Ly of x equal to the inner product of tx with y?
Oh, okay, so
Isn't it just x with y?
sorry, we haven't used Riesz's representation theorem yet. I've just defined this way. So then what we have here then is I have Ly, which is a bounded linear operator. And I also have that,
He gives a thumbs up.
okay, good. Yes, yeah. So then what this tells me then I have a bounded linear operator Ly. And I have that, so this belongs to the dual. But based off of Riesz's representation theorem, where it maps the K, which is real or complex, in my case, because inner products can be complex or have to be real always, I can then use Riesz's representation theorem, because then I have Ly. In this case, I've shown that bounded linear, so Ly is an element of the dual of H. Right? So that means by Riesz's representation theorem, Ly of x is equal to x comma y star. There exists some y star uniquely element of H such that any function that belongs to the dual of H can be represented as this inner product. Right? So that means then I have this equality. Ex comma y is equal to x comma y star. Right? But here you can see I have px, I don't have x here, right? What I can then just do is that I can just define p star of y to then just be equal to y star. Right?
Why'd you go so hard on that? When you said like a trillion lines.
So I just wanted to make sure that it's visible. Right? So then what I have here then is that I have ex comma y is equal to x comma p star y. Right? So Riesz's representation theorem immediately for free gives me that the adjoint exists, and I can even complete what the adjoint is.
I don't like that line right above the equality. Is that the definition of T star Y?
Yes, so, yeah, p star y is defined to be equal to y star. So therefore, ex comma y is equal to y star, y star is equal to p star y. So this is equal. Now I can uniquely move t over to get this, but then it's always uniquely defined, right? Upper Riesz's representation theorem, right? So adjoints always exist for bounded linear operators.
-5 minutes.
Sorry?
-5 minutes.
Negative 5 minutes. Okay, I'm gonna stop there. Kind of sucks is I didn't get to go over a bunch of other interesting things.
You can always give another seminar part two.
Yeah.
Would you guys be interested in the second seminar? It would be
Yeah, yeah.
generalized Fourier series.
Yeah, because it seems like you have enough material for another talk.
Oh, yeah.
Seeing your the amount of pages you have in
Yeah,
your
I still have
hand.
a lot. And you know what? How would I also add in the resolvent stuff?
Yeah.
Sure.
Yeah.
Yeah.
good. But when you say generalized Fourier series, you mean
I can go right.
series or-
How would I just do a little taste of what I mean then?
Sure, yeah.
Okay. So what I can do is I can introduce this idea. So orthonormal sets, that's kind of what we always do. We say, oh, we can expand everything in terms of orthonormal sets. In the finite dimensional case, you can always do that, right?
So before you read that, I just wanted to point out that I think it's a wordly common,
Yeah.
is that H and H star is not an isomorphism of complex vector spaces, right?
No, there was Hilbert spaces and then bounded linear operators from H to the reals.
So the thing that you wrote that H is isomorphic to H star.
Yeah.
That is not an isomorphism in the complex category. Because it says collinear, right?
Cool. Sorry, I'm not too familiar with any of that.
Oh, okay. What I'm just trying to say is like the isomorphism you pointed out about
Yeah.
H and H star.
Yeah.
It's not it's not an isomorphism of complex vector space. In the right.
What kind of isomorphism is
Yeah,
it?
what kind of
Because it's a
isomorphism?
non-canonical isomorphism,
The
right?
thing is like it's not linear. It's not complex linear because you're gonna have if you look at the inner product, it's complex linear on one side.
Oh, yeah.
So it's gonna have bars. So it's not a proper isomorphism.
Oh, okay.
Then that's important, like if you do complex geometry, when you try
Uh-huh.
to do these things, you guys have to keep track if you talk about complex vector bundles that you have like the bars in the right place.
So what would that isomorphism call?
Usually call it collinear.
It says collinear.
Yeah.
That's collinear. Yeah. I've ever heard that. Sorry, I should have been
And it's
Yeah, okay.
non-canonical. Oh no, it's canonical, right?
No,
No.
yeah,
You mean canonical, you mean natural or
Uh,
canonical?
as in like for each element in H, there's a canonical choice for in H bar that is isomorphic to.
sure.
In this case, yeah,
Because you have, well, if you don't have a metric, then it's non-canonical. But but now you have a inner product induced norm. So from inner product, that is the metric. It has the metric, so it becomes canonical in that case. Yeah, because it's a Hilbert space.
Yeah, but here was the word becomes.
oh, absolutely, yeah, thank you so much.
Is actually not working and you're kind of.
So suppose I have a set of orthonormal, an orthonormal sequence. So in this case, the reason why I want an orthonormal sequence is because I want it to be countable. But everything I'm about to talk about can be defined for uncountable sets as well. Essentially, you just change this to J, but just J, which can be countable, not uncountable. But let's just work with countable. Just make it a bit easy. So then if I'm in X comma inner product, so I'm in an inner product space, and these are all orthonormal. So then what I can say then is, yeah. So for all X an element of X, I can say that it's Fourier, I guess I can call it Fourier decomposition of X comma EK, EK. This is going to converge to something. So this converges. I don't know what it converges to, but I can show that it converges. And I have that the norm of the coefficients squared, sum over them, is bounded above by the norm of X squared. So essentially what I have here is an orthonormal set. I've decomposed X, or I've done this decomposition essentially, which is actually just a projection, but right term is we call this projection. Given by inner product of X comma EK. This is what we do with orthonormal sets all the time in quantum, in linear algebra all the time, right? But in this case, just being an orthonormal set doesn't give me an equality in an dimensional case. If it was finite dimensional, sure, absolutely, I would actually get equality, right? In this case, Bessel's inequality, the best I can do here. It is bounded above by the norm. Therefore, this here is not actually, this doesn't actually equal X in this case.
I think it doesn't converge to X.
It doesn't converge to It converges to something, right? What we ended up saying that is that this converges to the projection of X onto the space given by the span of the set of EI, I, the closure of it. So this, yeah, right? So again, I've said basically nothing interesting here. I've written this span, right? Taking an infinite, so taking a limit, right? So then I'm taking a closure of this, meaning this contains all of its limits. So this here is an element of here, right? But based off of Hilbert's projection theorem, this is a closed subspace, correct? So that means H can be decomposed as a direct sum of this span of EI, I, orthogonal complement, right?
Yes.
So then if I want to be able to write that this is actually equal to X, right? That means H has to be equal to this term, and this term here has to just go to the empty set, right? Or zero set,
Yeah.
right? Right, so it means I need some extra structure on my orthonormal set, right? That's where we introduce this idea of maximal orthonormal set. And how do we define a maximal orthonormal set? It's the set of orthonormal vectors here, such that H is just equal to the span of EI, I, closure, plus this part, but it's just equal to zero. It does not. Right? This is the definition of orthonormal sets.
And
Right.
you said that this works for the uncountable case?
Yeah, it also works in the uncountable case. But
The exact same definition, I mean?
same definition of it. Okay, yeah. So yeah, and then the question is, well, you probably no one's ever talked about maximal orthonormal sets, right? So when you're working with your position operator, your momentum operator. You're not working with just orthonormal set, you're working with maximal
Oh,
orthonormal
that's a good
sets.
point, actually. Oh,
Yeah, right?
yeah.
Right, finite dimensional cases, orthonormal set is maximal, right? So then the question is, okay, kind of going through some, like, I'm going kind of fast with this, but easy question you could ask is, okay, well, how can I determine if something is a maximal orthonormal set? Right? The way you do it is you just show that the perpendicular is equal to 0, right? So a sufficient way of doing that is with this, yeah, there. So the set I is maximal orthonormal if and only if you have the situation x comma, I know it's an if and only if you have this situation x comma e k equals 0 for all k, then the only way this is possible is if x equals 0, right? So essentially what I've done here is said, okay, if I have some element which is orthogonal to every element in this orthonormal set, if that's true, and I can show that the only element that satisfies this is x equals 0, then from here I can directly conclude that the orthogonal complement is 0. Therefore, I have h is just equal to the closure of this, right? Which is basically saying h can be always written as a limit of this span, is basically what this is saying. Remember, we've defined that you take a partial sum and then you take m goes to infinity. So this is the part where I'm talking about containing all the limit points. So h can be always written as an infinite sum of these elements here, right? And this is only true if our set EI here are maximal orthonormal, right? And in the case of spectral decomposition, you have a self-adjoint. So if you have a bounded linear operator, which has an adjoint exists based off of that theorem over there, where the adjoint exists for bound linear. If on top of that you have that T is self-adjoint, then you can always create this orthonormal set that is maximal, right? In that, and the only case where that is, you can always make an orthonormal set. The only time it is ever maximal is if it never has a 0 eigenvalue. So then I just want you to think about it. What's the 0 eigenvalue of the position operator? What gives you back 0? 0, right? So that, so then does that have a 0 eigenvalue or? Right, no,
Well,
x hat,
okay, yeah.
x is never equal to 0 unless plugging the 0 vector,
And
right? So then, again, this will be something I prove, I don't know, next
time here.
right? I can show that that's the case. It's 0, the eigenvalue is never 0. Therefore, you have a maximally orthonormal set, which means you can decompose everything in terms of those eigenvectors.
Yeah.
Yeah. Lonnie?
It's only in, you said.
Yeah, it's only an EI.
For the thing with the operator.
One direction, I think, sorry. If the eigenvalue is non-zero, or if lambda equals 0 is non-eigenvalue, then the orthonormal set is maximally.
Yeah, so you can talk about it in terms of singular values, like if we have singular values, you know? Like, sorry, singular as in 0.
Sorry, for SVE?
No, similar thing in QT2, like we were talking about the spectrum stuff, and we didn't talk about eigenvalues. We talked about like 1 minus the eigenvalue, because you always write like I minus lambda.
Oh, you know what, how about, let me talk about the resolvent real quick.
Okay, is that the resolvent then?
Like
what I just said, I think?
No, okay, the resolvent is a little bit more finicky. This is one thing I hate. I hate that Augerman puts this in his chapter 4.
Dude, it's like 2
Because it doesn't,
paragraphs.
it's 2 paragraphs. It doesn't explain anything. I still remember when William went to an office hour to talk to him about this stuff, and then it just came down to, I just showed it in functional analysis, and that was the extent of an answer. So what we define is, okay, we have some operator T, right? So we define T lambda to equal T minus lambda I, right? So this is basically your eigenvector equation, right? So then we define that the resolvent R lambda T equals T minus lambda I inverse, right? So then what we have here is, okay, well, under what cases, so then this is what we call the result, right? And then what we have is we can figure out, so it's a function of lambda essentially, right? T is given, right? So we can change lambda around. So first and foremost, P minus lambda I, right? If X is an eigenvector of P, right? So let's say that lambda I is an eigenvector, so Tx equals lambda I x, right? So if I plug in lambda equals lambda I, then I have that Tx minus lambda I x. So plugging in lambda equals lambda I, or I'm saying lambda I is an eigenvalue, right? Then this equals lambda I x minus lambda I x, which equals 0. Therefore, I have a non-trivial kernel, right? Non-trivial kernel means I can't be injective, right? Which means the inverse does not exist, right? So for all lambda elements of the complex numbers, such that T minus lambda I inverse does not exist, then we say that lambda is an element of the point spectrum of T. Essentially, the point spectrum are just your eigenvalues, which you know and love from linear algebra, right? But then you get into these two new special cases. And then I'm going to make a little chart for them. So you have R lambda of P, which equals P minus lambda I inverse. So it exists. You have that the domain of the range. No, sorry, the domain of R lambda and P, its closure is equal to X, and then you have R lambda P bounded. So these are three cases you can have in your problem. So what we've shown here is that if you're using the natural eigenvalues, it means that the inverse does not exist. If the inverse doesn't exist, the function isn't going to exist. So these are just not applicable and A. So this is what we call sigma P, the point spectrum. Then you have that R lambda P minus lambda I exists. Yeah. You have R lambda P exists. R lambda, so the domain of R lambda P, its closure is equal to all of X. Exists. And then that it's also bounded. So this is called the resolvent set. This is where basically you keep all the nice properties of the resolvent bounded. It's vector and surjective, and then its inverse exists. Then you have another case where the inverse exists. This doesn't hold true, and this one you just don't care anymore because this property doesn't hold. You don't care too much about this one, and I think this one is the. I think this is the resolvent set. Okay. Or maybe this is the finite set. And then the next one is you're bounded. You have this property, but you're just not here. And then I think this one is the sigma R. And then you would say that the spectrum is equal to the union of sigma C union sigma R union sigma P. I may have these backwards. I just don't remember which one is which. But essentially, this is the property.
Maybe it should be swap.
Should we swap it?
If I remember.
Yeah, it's whatever. I'll bring this up next time. I have a pretty easy example with for P from L2 to L2, where you can show this exists, this is empty, and this exists. Simple enough example, but essentially, yeah, these are like the three cases or four cases. Right, so this is what we call the resolvent set. This is basically where everything is nice, everything is perfect, right? And then once you start breaking some of these properties, you're introducing new cases, right? And then yeah, so your point spectrum is basically your simple eigenvector problem. The resolvent set and the continuous set is basically just their names come from when you think about like energy and stuff like that, you need the energy spectrum, and
Yeah.
then the result is that one. That's kind of complicated to talk about. I don't have a physical intuition behind it, but essentially, I'm pretty sure this one for self-adjoint operators in Hilbert spaces is always in. So because we always work with observables that
For
are,
like degenerate,
yeah, I think
I think
it's
it has to do with like degenerate energy spectra, but I don't really care about the physics of it.
yeah, but essentially this one is almost always zero because you're working with dimension operators.
Yeah.
Right, you can actually show that. Right, and then this I'll talk what you guys want me to. I have some simple examples, we'll go through these, but yeah, and then a big thing that I didn't get to talk about is I think I brought up with the whole connected complex analysis. Because I have this definition R lambda of T equals T minus lambda I, what I can basically do is with the whole using operator norms and Lebonic space and all of that stuff, you can actually kind of think about Taylor expanding around point spectrums and stuff. So you can do like a Taylor series around lambda minus lambda naught n of some operator which we'll call A for the end, northern factorial. And like you take Taylor series of it, 0 to infinity. So again, kind of taking a Taylor series of operators and stuff, and have to kind of define what all
To the -1 first. The
T minus lambda I inverse.
it should be the inverse.
Oh, sorry, yes, absolutely. Yeah, absolutely right, absolutely. Right, so what I can do is kind of rewrite this as a Taylor series, and then what I can do is, well, A is just an operator, right? Just an operator, right? Doesn't depend on lambda. So then what I have here is I basically have a function over complex lambdas. I can do some complex analysis. You can actually do residues on this, right? And then basically looking at the poles, doing the Laurent
Would that
series.
just depend on A? The poles, because
so-
minus lambda not to the end has no poles.
Yeah, sorry, so what you would do, sorry, here you take this from negative infinity.
Ah,
Yes,
okay.
And then what you have is you have like one
Yeah,
minus lambda
yeah,
minus lambda naught. And then this operator here for this specific value is actually going to be a projection onto this eigenspace.
That'll be your residue.
Right, so that's your eigenspace for lambda naught, right? And then you just have to figure out where the heck this is coming from, right?
Yeah.
So you just basically do a residue integral, is just 2 pi I or something, then you get for free essentially.
Yeah.
Right. Okay, so again, we can solve it as like a complex analysis problem. Okay, lost over some stuff here. We got a lot of stuff here, but yeah.
Just a little bit.
A little bit.
Are you proposing to like define R lambda on some of these like subsets of stuff?
Yes, exactly. So the idea here is that all of these spectrums are defined based off this R lambda T minus lambda I inverse, right? If it doesn't exist, you get that for free. If it does exist and it satisfies these properties, then you get the other special cases.
Right. Are you saying that like the domain of R lambda still
Is this
still
the
contain
rate?
any sets? Or are you saying we should expand it to contain one of these on the bottom 2 sets?
Sorry, what do you mean by the domain of R lambda? These sets here are just the lambda values. The spectrum is just lambda.
Like, I mean, I guess you're writing here like this inverse exists. Like,
Yeah.
I guess it's like it's only like injective, but are you? I guess I'm only asking this because I've seen like in like if you're thinking of things like operator algebras, like you're thinking of just having algebra operators and you don't have the space, then you can't think about like you need to throw out all of these other spectrums or subsets of the spectrum. You can't define R lambda on those, right? Because you can only invert it when it's like invertible in that algebraic sense.
I'm not too familiar with algebras and stuff.
No. Okay, but just like here, you're saying R like in the bottom left wing check marks.
Yeah.
Or bottom 3, I guess.
Yeah.
Okay, but wherever you're saying R lambda T exists,
Yeah.
like this function t minus lambda I is injected, so you can come up with an inverse on its domain, is what I'm saying.
Yeah.
But you can't actually, it's not a true inverse of between the spaces.
No.
Yeah, that's what I'm saying.
Yeah.
So like, are you saying we should like, is this something you usually do in physics where you talk about the R lambda t function? You
Just on the like.
Yeah, so here.
yeah. Well, it just looks like you're like like you're saying we're defining the function on more than just the complement of the spectrum.
Mhm.
Oh, it should be restricted. It can't be the whole thing. Or should it be the whole thing?
I don't think you can.
Like, yeah, I don't think it can be the whole thing, right? Yeah.
You have to restrict it to the appropriate subset.
Yeah.
Yeah.
I think that might just be like a given type of situation. You only define it on the
Image of
restriction.
of t lambda. T lambda equals t minus lambda I. So yeah, then you would say that R lambda defines on the image of t lambda
Yeah.
to like where the heck it's gonna end up going.
Yeah.
Sure, but I'm not talking about I'm not talking about the domain in like the operator algebra.
Yeah.
I'm talking about the domain on the in C.
And see, oh, you're talking about lambdas.
Yeah.
Okay. Yeah, so
Sorry.
yeah. Okay. So then what's your issue with this?
No, I'm just asking like
Oh,
as like an issue of culture. Like do people usually consider this R lambda function as like
yeah, so this is
it's like think of it as R sub T lambda.
Lambda,
right?
yeah.
Lambda.
Oh, I see what you mean. I see what you
It's
mean.
like- yeah.
So then, yeah. So from what I see is this is the notation I've seen, and the idea behind it is that you're basically given an operator T, right? So this would be your
So it should be considered as a
function of lambda. Of lambda only. Yeah. T is given. T is given.
Yeah.
Sorry.
So it
Essentially,
should, I don't understand why it's not RT of lambda.
I don't know. No, I guess because I don't know. I guess you go either way.
Yeah.
I guess in this case, the idea here was that I guess it's, yeah, just up to notation.
But then-
I've seen it this way. I agree. This is also.
Yeah, but then the question is like, when you talk about inverses and whatnot, it should be on
Right.
stuff of lambda. We should
Yeah.
be talking about images of T, but more so
Yeah.
lambda, where lambda's on which is C.
Yeah, in this case,
It's strange, like to like if you okay now we're thinking about it as a function R sub T of lambda.
yeah.
Okay,
Yeah.
this domain is in C somewhere. It's a
Yeah,
subset
yeah.
of C. It's not all C.
Yeah.
But if you're saying it has
The spectrum.
yeah, there's some of its domain contains the spectrum
Yeah.
of its operator, then it's weird because you're mapping like its image now is not in like
operator.
it's not an operator space.
It's now in C.
Yeah.
It's because you're gonna have like some operators with different domains. Like some of them, if you're in the complement of the spectrum, you'll have the operator do some you get will have their domain will be like a whole space.
Mhm.
But otherwise it's gonna have like some small.
Yeah, but that's for different operators.
Yeah.
But that's what you would do usually. You would
Yeah,
say,
Yeah.
Yeah, right. So then the interesting cases here would be, again, just going back to like linear algebra and stuff, right? Like if you're talking about normal matrices, Hermitian, self-adjoint, like energy, Hamiltonian and whatnot, right? And observables, right? If you use this sort of language, then okay, the resolvent one always goes to zero, but then these two don't have to be, right? And then this is basically just the complement of these two. So lambda is always going to be in one of these three.
Well,
But then for different operators, we choose
okay,
different
so
things.
William recently sent a paper in there that was talking about observables which are non-Hermitian. They're just like a joint or something, or
Normal.
normal.
Yeah.
So do those coincide? Like like
So non-Hermitian mean that you have complex eigenvalues, right?
yeah,
Right,
but
so then-
the paper I was reading, I only read the title, so I could just be completely
Yeah.
misinterpreting it. But in the abstract, it talked about how you can have observables that are just normal. So should all observables have the same spectrum, or do like normal and Hermitian have different spectrum?
They have different spectrums for sure.
Really? Okay. Huh.
It
Okay,
just,
I definitely have to look into this more.
Yeah, again, I don't have. this part here, the only example I have that where I can basically compute these really, really easily is from L2 to L2, where essentially I take this map, E of x1, x2, x3, dot. If map to lambda 1, x1, lambda 2, x2, dot. And I can show that it has a point spectrum. I can show that it has a continuous spectrum. And I can show that this spectrum. Because this is if lambda 1, lambda 2 are real, it's self-adjoint. I can show it, right? And then in this case, I've never heard of observables as being non-Hermitian.
It was really weird. I want to read that paper. So I think someone just sent a message.
William said, I'm not an expert on this. Just remember Achim talking about it. He talked about it in office hours, and I guess Hermitian is a special case of normal.
If
I'm remembering, and Eduardo also does this as well. But in a lot of physics papers, they just take observable to be Hermitian.
But sure. I mean,
it just.
But technically, it's just normal.
Isn't that?
It doesn't have to.
That observables are Hermitian. That's an axiom. No. You can. You need real measurements.
With normal stuff, I think you also get real.
No, you get complex.
You don't?
You can get you can get anything.
Complex
complex argument. Hermitian is the only one that guarantees real.
So that's why I need to read that paper. I need to know what the heck that paper is yapping about. Observables that are just normal.
But you can have I guess you can say, we can observe complex values, but
maybe you say modulus. I mean, the other thing I was thinking is that all of its complex eigenvalues are somehow degenerate and zero. You can look at that. It still does have eigenvalues which could be complex, but they end up all being zero. That's just I don't know.
That's just
random idea.
I feel like this is trivially.
So it's still technically an observable, but I don't know. The other thing is, you can mathematically have complex observables, but it just doesn't physically represent anything.
We have normal things in our convention still have spectrum.
Also that,
you can have that as well. I'm sure there's examples.
William says, I think the paper is about how axiomatically you can use Hermitian or you can use all normal operators.
Oh,
axiomatically?
Pop it in there.
What's a physical consequence of?
We're probably not concerned with physics.
Oh, okay.
So
Classic.
He then says, so we usually work with the formalism of Hermitian, but you can do normal if you want to.
Okay.
Okay,
just the framework mathematically still works out to be.
You can do a lot of things if you want to in that.
So what is it? What does it mean if I have Hamiltonian, which is normal? If I have a imaginary eigenvalue,
That's
then I have a decaying generator?
He says, I don't know what it means.
That's
means in quotation marks.
Maybe your Hamiltonian is finite, there's just the potential overpowers it or something. It could physically represent that, or potential going to zero. Negative damping or
Is that you introduce quantum friction, air resistance or something? Because you'd be if I have an energy ket En, right, and then my Hamiltonian is e to the minus I h.
Your energy eigenvalues will have to be dependent on some of the position, for example.
Or something. It'd be like e to the minus I En En, right? But then if this is complex, under certain cases, this isn't
it also might not. It might also affect the time evolution too. That's weird. Anyway, whatever. I'll dabble in the paper later and see if I'm just. That's.
Oh, that's true. You don't even preserve probabilities.
Everything will just go to complete shit. That's weird.
Preserve probabilities.
Now, my stat 230 exam, so I'm scoring with 300% probability. That does remind me, on my stat 231, I think we were calculating. You know how you have confidence intervals. I got a confidence interval greater than 100%, greater than my entire Gaussian. I'm like, ah, perfect. Yes, truly the mean lies on the entire Gaussian.
Extremely confident.
Yeah, extremely confident. Or I also got like a p-value of, p-values are supposed to be like very small.
Yeah.
Whatever, I got a p-value of like 3. This is unbelievable.
That's unbelievably bad.
Yeah, that means that we're so confident that it's just not, it's not gonna work. Anyway, good.
Yeah, isn't the p-value like, what's the probability of you getting as bad of a,
No, it has to do with the confidence interval. What's the probability that your estimate lies inside of the confidence interval? And so the p-values are inverted. So
Yeah.
a very low p-value means you're very confident
Very
because your
confident, yeah.
interval is very, very small
Yeah.
around your estimate. So it's like
Yeah.
almost very confident. The p-value is large, that means your interval of estimate is very large and your estimation, it could be anywhere in the.
Yeah, anywhere. The small p-value is what you want. I thought it was
Yeah, small, I know the small p-values are good. It means your hypothesis is, your null hypothesis is screwed. Okay. Good summary now.
Yeah, thanks.
Yeah, I forgot about it.